Let's solve this polynomial problem step by step. We're given that p of x equals ax cubed minus 11x squared plus bx plus c, where a, b, and c are integers. We have three key conditions. First, p of x is divisible by x. Second, when divided by 2x plus 1, it has a remainder of 3 halves. And third, p prime of 2 equals 18. Let's use these conditions one by one. First, since p of x is divisible by x, when we put x equals 0 in p of x, it should equal 0. This means that c must equal 0. For our second condition, we'll use the remainder theorem. When we substitute x equals negative 1/2 into p of x, we should get 3 halves. This gives us our first equation. Negative a minus 4b equals 34. For our third condition, we need to find p prime of x. The derivative is 3ax squared minus 22x plus b. When we put x equals 2 into this and set it equal to 18, we get our second equation. 12a plus b equals 62. Now we can solve these equations simultaneously. Let's multiply equation 2 by 4 to get 48a plus 4b equals 248. When we add this to equation 1, we get 47a equals 282, so a equals 6. Substituting a equals 6 back into equation 2, we get 72 plus b equals 62, so b equals negative 10. Therefore, we have found that a equals 6, b equals negative 10, and c equals 0. For part b, we know that x is a factor, and 2x plus 1 gives remainder 3 halves, so it must also be a factor. The third factor must be 3x minus 5 to make the polynomial complete. Therefore, p of x equals x times 2x plus 1 times 3x minus 5. To verify this is correct, we can expand it out and check that it matches our original polynomial with the values we found for a, b, and c. Let's solve this vector problem step by step. We're given 2 points, a and b, with their position vectors. Let's first visualize these points on a coordinate plane. Here's our coordinate system. Point A has position vector 2, negative 6, shown here in blue, and point B has position vector negative 3, 6, shown here in red. For part A, we need to find the displacement vector from A to B. The displacement vector is found by subtracting the position vector of A from the position vector of B. For part B, we need to find the distance AB. The distance is the magnitude of the displacement vector, which we can find using the Pythagorean theorem. Taking the square root of negative 5 squared plus 12 squared gives us 13. For part C, we need to find point x, where 3 times vector AB equals 2 times vector AX. This means x divides AB in the ratio of 2 to 3. We can find x's position vector by first calculating AX as 3 halves of AB, then adding this to A's position vector. Let's calculate x's position vector. First, AX equals 3 halves of AB, which gives us this vector. Then adding this to A's position vector gives us x's position vector, negative 11 halves, 12. And there we have it. We've found the displacement vector AB, the distance AB, and the position vector of point x that satisfies the given ratio condition. Let's solve this logarithm problem step by step. We'll start with part A, where we need to write 3 log x minus 1/2 log 4 plus 2 as a single logarithm to base 10. First, let's recall the properties of logarithms that we'll use. The power rule states that n log of a equals log of a to the n. The product rule states that log of a plus log of b equals log of a times b. And the quotient rule states that log of a minus log of b equals log of a over b. Let's apply these properties to our expression. First, using the power rule, 3 log x becomes log of x cubed. Next, negative 1/2 log 4 becomes negative log of 4 to the 1/2 power, or negative log of 2. And plus 2 can be written as log of 10 squared, or log of 100. Now, we can use the product and quotient rules to combine these terms. This gives us log of x cubed times 100 divided by 2, which simplifies to log of 50x cubed. Now, let's move on to part B. We need to solve the equation 2 log base of 4 minus 3 log base 4 of a minus 5 equals 0. First, we'll convert log base 4 of a to base a using the change of base formula. Log base 4 of a equals 1 over log base of 4. Substituting this back into our equation, we get 2 log base of 4 minus 3 times 1 over log base of 4 minus 5 equals 0. Let's let y equal log base of 4 to simplify our work. This gives us 2y minus 3 over y minus 5 equals 0. Multiply all terms by y to clear the fraction, and we get 2y squared minus 5y minus 3 equals 0. Using the quadratic formula, we get y equals 5 plus or minus the square root of 49 over 4. This simplifies to y equals 3 or y equals negative 1/2. Remember that y equals log base of 4. For y equals 3, we get a cubed equals 4. So a equals the cube root of 4. For y equals negative 1/2, we get a to the negative 1/2 equals 4. So a equals 1/16. Therefore, the solutions are a equals the cube root of 4 and a equals 1/16. Let's analyze a curve given by the function f of x equals the product of 2x plus 1 and 3x minus 2 squared. Let's start with part A, finding the derivative. We'll use the product rule, since this is a product of two functions. The product rule states that the derivative of u times v equals u prime times v plus u times v prime. Let's find u prime and v prime separately. U prime equals 2, and v prime equals 2 times 3x minus 2 times 3, which is 6 times 3x minus 2. Now, let's substitute these into the product rule. This gives us 2 times 3x minus 2 squared plus 2x plus 1 times 6 times 3x minus 2. Let's factor out 2 times 3x minus 2. After factoring and simplifying, we get 2 times 3x minus 2 times 9x plus 1. For part B, we need to find the stationary points. These occur when f prime of x equals 0. Setting our derivative equal to 0, we get either 3x minus 2 equals 0 or 9x plus 1 equals 0. Let's create a graph to visualize this function. For part D, we need to find values of k, where f of x equals k has 3 distinct solutions. This occurs when k is between 0 and 343 over 81, the y-coordinate of our local maximum. And that completes our analysis of this curve. We found its derivative, stationary points, graphed it, and determined where it has 3 solutions. Thank you for watching. Let's solve this problem involving a curve, a line, and their intersections. We have a parabola given by y equals 4x squared minus 6x minus 5, and a line y equals 1 minus 4x. We need to find where the tangent at one of their intersection points meets a horizontal line. Let's visualize this. Here are our axes. Here's our parabola, y equals 4x squared minus 6x minus 5. And here's our line, y equals 1 minus 4x. First, let's find the intersection points. We set the equations equal to each other. 4x squared minus 6x minus 5 equals 1 minus 4x. Rearranging, we get 4x squared minus 2x minus 6 equals 0, or 2x squared minus x minus 3 equals 0. Using the quadratic formula, we get x equals negative 1, or x equals 1.5. These give us our intersection points A at negative 1, 5, and B at 1.5, negative 5. Now for the tangent at point B. The derivative of our curve is 8x minus 6. At x equals 1.5, this gives us a slope of 6. So our tangent line has equation y equals 6x minus 14. Finally, we draw the horizontal line through which has equation y equals 5. To find point C, we solve 6x minus 14 equals 5. This gives us x equals 19 over 6, or approximately 3.17. Therefore, the x-coordinate of point C is 3.17, correct to 2 decimal places. Let's solve this arithmetic progression problem step by step. We're given that the first 3 terms are negative 3 tan theta over 2, negative tan theta over 2, and tan theta over 2 where theta is between 0 and pi over 2. Let's start by finding the common difference d. We can find this by subtracting any consecutive terms. Let's use a 2 minus a 1. This gives us negative tan theta over 2 minus negative 3 tan theta over 2, which simplifies to 2 tan theta over 2. Now, we know that the 12th term equals 19 root 3 over 3. Using the arithmetic sequence formula, a sub n equals a 1 plus n minus 1 times d. We can substitute n equals 12. Let's solve for theta. From our equation, 19 tan theta over 2 equals 19 root 3 over 3. Simplifying, we get that tan theta over 2 equals root 3 over 3. Taking the inverse tangent of both sides, theta over 2 equals pi over 6, therefore theta equals pi over 3. Now for part 2, we need to find the sum of the first 10 terms. We'll use the arithmetic sequence sum formula. S sub n equals n over 2 times 1 plus n minus 1 times d. Let's substitute n equals 10. A 1 equals negative 3 tan theta over 2, which we now know equals negative root 3, and d equals 2 over root 3. Let's simplify this expression. 5 times negative 2 root 3 plus 18 over root 3 equals 5 times 4 root 3, which gives us our final answer, 20 root 3. And there we have it. We found that theta equals pi over 3, and the sum of the first 10 terms equals 20 root 3. Let's solve this geometric progression problem step by step. We're given the first 3 terms, 1/16 cosec to the 4th phi, 1/4 cosec squared phi, and 1. First, let's find the common ratio r. We can find this by dividing the second term by the first term. This simplifies to 4 cosec squared phi. Now, we're given that the sum of the third and fourth terms equals 4. The fourth term is the third term times r, so we can write 1 plus 1 times r equals 4. Solving this equation, we find that r equals 3. Now we can substitute this back. 4 sine squared phi equals 3. Solving for phi, we get sine squared phi equals 3/4. Taking the square root, sine phi equals plus or minus 2 over root 3. Given that phi is between negative pi over 2 and positive pi over 2, the possible values for phi are pi over 3 and negative pi over 3. For part 2, we need to determine if this progression has a sum to infinity. A geometric series has a sum to infinity only if the absolute value of r is less than 1. Since r equals 3, which is greater than 1, this series does not have a sum to infinity. To summarize, we found that phi equals plus or minus pi over 3, and we determined that the series diverges because its common ratio is greater than 1 in absolute value. Let's solve this calculus problem step by step. We're given that y equals the square root of 3x squared minus 2, all divided by x minus 4. We need to find dy dx, and show it can be written in the form ax plus b divided by the quantity x minus 4 squared times the square root of 3x squared minus 2, where a and b are integers. To solve this, we'll use the quotient rule. Remember, the quotient rule states that the derivative of u over v equals v times du dx minus u times dv dx, all over v squared. In our case, u is the square root of 3x squared minus 2, and v is x minus 4. First, let's find du dx. Using the chain rule, du dx equals 1 over 2 times 3x squared minus 2 to the negative 1/2 power, times the derivative of what's inside, which is 6x. Next, dv dx is simply 1, since v is just x minus 4. Now let's substitute everything into the quotient rule. This gives us x minus 4 times 3x over the square root of 3x squared minus 2 minus the square root of 3x squared minus 2, all over x minus 4 squared. After simplifying the numerator, we get negative 12x plus 2 over x minus 4 squared times the square root of 3x squared minus 2. Therefore, a equals negative 12 and b equals 2. For part b, to find the approximate change in y when x increases from 3 to 3 plus h, we use the formula that the change in y approximately equals dy dx evaluated at x equals 3 times h. Evaluating dy dx at x equals 3, we get negative 34 over 5. Therefore, the approximate change in y is negative 34 over 5h.